This is a re-recording of page 7 of our notes, so that way we can have some sound to this, some audio to this. And we're starting off with elevator problems. And the basic discussion is, when is the tension in the elevator cable the greatest, and when is it the least? And then also to draw a free body diagram of an elevator in the space below. And so when the tension is the greatest, is probably when we have to catch it from falling, right? Or when we're trying to get it to move faster and faster up. When tension is the least is when we are starting to go down, and so we can just kind of let go and let it fall under gravity, and loosen our grip of it. Think about maybe your hand being right here, so that's your hand, grabbing onto that rope and being the device that pulls up. And so when are you really pulling the hardest versus lightly? And so to show that, when it's pretty much, when do we have this interaction? That's when we have to pull the hardest. And that happens at 2 times. If it's like falling and we want to keep it from falling, we're going to have to pull up a little bit harder. Or if, gravity is the same, when we don't pull as hard is when it's moving up and it comes to a stop. Or when we let go of it to let it move down, and we kind of just guide it gently down. So the process rule, the direction of the acceleration is going to be positive. That's a key important part. That's the whole reason why I need to re-record these, is because if you miss that step, then everything else we're doing is pretty difficult. Any force that goes opposite the direction of how it's accelerating will be negative. And we don't use gravity as negative. We choose it once we set up our acceleration. So if it accelerates up, gravity would be negative. But if it's accelerating down, downward becomes negative. And therefore, this gravity is actually, so down is now positive because the acceleration is down, and that's positive. Gravity then becomes positive, and the tension pulling up would be negative, okay? As long as there's a tension pulling up. So, sample 1. An elevator has a mass of 1,000 kilograms, right? 1,000 kilograms. Solve for the tension in the cable when the elevator is at rest, when we have a speed going up, a speed going down, an acceleration going up, an acceleration going down, and the cable breaks. And so part A, when the elevator is at rest, we draw our elevator, gravity pulls it down, and holding this up is the tension. So force due to gravity, tension. If it's at rest, the down is balanced by the up. If it's at rest, the net force equals mass times acceleration, but at rest means that's 0. And so the force is 0. Also, when I look at my picture, my gravity going down is offset by my tension going up. And because neither of those is the way the box is moving, we can just say up is tension and down is gravity. Or we could say down, up, positive is gravity, and negative is tension. That's possible too. Because when this equals 0, we can move 1 to the other side. Tension equals gravity. That's what keeps it from accelerating up or accelerating down. Well, Fg is mg. And so if Fg is mg, we know that it's 1,000 times 9.8. 1,000 times 9.8 is 9,800 newtons. So our tension is 9,800 newtons. What's kind of crazy is that this F equals ma relates it to the acceleration being 0. And if I have a velocity at 3 meters per second, And then later on, I'm still looking at a velocity of 3 meters per second. And by the end of the problem, I'm looking at a velocity of 3 meters per second. The acceleration, it didn't speed up, it didn't slow down, it's at 3 meters per second. So the acceleration is still 0. That one equals 0 as well. And so this drawing is not just for portion A, but it's also good for B and C. We do need to solve for a different thing in part D. In part D, we have an acceleration up. And so my net force equals ma, and this a is non-zero. It's 3. In fact, that's 1,000 times 3. That's how it's going to move. Our picture, we have a tension, and this tension has to pull up greater than the gravity of our last problem. So much so that tension overcomes gravity and gives us the leftovers of this 1,000 times 3. In other words, for my net force equation, I have my picture of, well, it's moving up, so I'm going to make tension positive and gravity negative. And this net force is the ma, and gravity is mg. We know that we have the 1,000 times 3 equaling tension minus 1,000 times 9.8. So we really have 3,000 plus 9,800 equals the tension, right? This is ma plus mg equals T. That would be kind of the summation of my tension equation. And what that really means is that even though tension is up and gravity is down, there's an overall net force that is up. This is the way it accelerates, ma, and so tension is long enough to overcome gravity and give me this leftovers. This plus this, but it's negative, equals this. If I were to take this and move it over here, you could see that it adds up correctly. Okay, so that's part D. 12,800 newtons. Part E says we're going to accelerate downward. And so now, in my net force equaling ma, if I were to redraw the picture, I have gravity going down, but now to accelerate downward, I'm going to have a tension up that doesn't pull hard enough. So instead, this is going to be force of gravity. Why? Because it's generally moving down, so gravity is positive. And I'm going to subtract off tension from that. And we have ma equals mg minus t. So t equals mg minus ma this time. Instead of plus over here, it's a minus. So we have 1,000 times 9.8 minus 1,000 times 3. That's the same thing as 1,000 times 6.8, or 6,800 newtons. 6,800 newtons. And that's for part E. Lastly, part F, our free body diagram, is that there is no up arrow, right? And so for part F, we have Fg, but tension equals 0. It asks us for the tension, so I don't even need to solve for anything. But gravity is also equal to the net force because tension doesn't exist. or tension is 0. 2, a man that has a mass of 100 kilograms weighs himself in an elevator on a scale calibrated in newtons. What will the scale read in the above scenarios? So the scenarios are very similar, except instead we have a man standing on a scale in an elevator. So what are we really weighing? Instead of tension, his gravity pushes him down, and not tension, but the normal force on the scale holds him up. So that scale is actually getting pushed down, and that contact force is what it's reading. And what's crazy about that contact force is it's relative to tension in all of these. If this person, I'm going to redraw that person like a free body diagram. If that person is accelerating up, it's the floor that's pushing him up, but gravity is still the same. But now the normal force, the ground, is pushing him up, and so he moves up with the ground, and that arrow is bigger. If he were to accelerate up, the diagram is the same, so the math is the same as the sample above in part 1. You would have 980 down, but just like in part D, to accelerate up, he would have MA equals force normal minus force due to gravity, and that's mg. That's the net force, and so all the math is the same. The only thing that's changed is 10 times smaller for all the answers, and instead of tension, we call it force normal. I'm going to put force due to gravity right here because that's the gravity right here. But of course that means 980. That force normal will equal the 980 plus this 300 on this side. This up arrow is 1280. Alrighty, catch you on the flip side.